Hello everyone. So welcome to the last lecture of this module, and it is the last lecture of this course also. So in this lecture I will talk about multi-step method for solving ordinary differential equation numerically. So in the past few lectures we have talked about Euler's method and then Runge-Kutta method of order 2 and order 4. So in all those methods, like in Euler's method, we have taken our approximation of y at x equals to xk plus 1 as yk plus h times f of xk yk. So here we are assuming that our x equals to xk, and at xk yk the value of y is yk, and these two values are known to us, and from these two values we are moving to the next value of y at next point, that is yk plus 1. In the same way, in the Euler's Runge-Kutta method, what we have done, we have calculated the value of y at x equals to xk plus 1 as y at x equals to xk plus k, where k is coming from the average of k1 and k2, and k1 is given as h time f of xk yk, and k2 is given as h time f of xk plus h yk plus k1. Now please look here that for finding the value of y at x equals to xk plus 1, that is yk plus 1, we are using the value of y at x equals to xk and xk and yk. So for finding the value in the next approximation or in the next iteration, what we are doing, we are using only the value of current iteration. Similarly, we are doing the same thing in Runge-Kutta method. So here we are moving one step, that for finding the value in the next iteration we are taking the value of current iteration only. However, in multi-step method we will use the value, not only the value of current iteration, but we will use values of some previous iterations also, like the value at x equals to xk minus 1, at x equals to xk minus 2, and so on. And that is why for calculating the value of y at x equals to xk plus 1, we are using value at kth iteration, in k minus 1 iteration, in k minus 2 iterations, and that is why it is called multi-step method. So the principle behind a multi-step method is to utilize the past values of y and or derivative of y to construct a polynomial that approximates the derivative function, and then extrapolate this into the next interval. So basically, using 4 to 5 points we will construct or approximate a polynomial of degree 4 or 5, and for the value of in the next iteration or at the next point we will extrapolate the value using this particular polynomial. So the number of past points that are used sets the degree of the polynomial which we are going to approximate or going to fit, and is therefore responsible for the truncation error. The order of the method is equal to the power of h in the global error term of the formula, which is also equal to 1 more than the degree of the polynomial. So if we are having 4 degree polynomial, we will be having the error of order h raised to power 5. So generally, using an implicit linear multi-step method, there is an additional difficulty because we cannot solve simply for the newest approximate y value, that is y n plus k. So because we are having an implicit formula, and here we are having the value of y at x equals to xn plus k in left hand side as well as in right hand side, and hence how to get out the value explicitly, that is the problem here. So, a general k step implicit method involves at the k time step by this equation. So, alpha k yn plus k plus like that, alpha 1 y1 plus alpha 0 y0, and this is equals to h times beta k f of n plus k plus beta 1 f1 plus beta 0 f0. So, now here you can note down that here in this equation I am having the value of yn plus k in the left hand side and fn plus k in the right hand side. Basically this fn plus k is also involving the term yn plus k, because fn plus k is f of x n plus k, that is n plus k times h into comma yn plus k. So, in this way we are having yn plus k in the both sides, and that is why we are saying it an implicit scheme. So, to get rid of this particular thing, one solution is to only use explicit method in which right hand side is 0, that is all betas are 0. However, this is not so good as an implicit method generally, but it can have a simplification in terms of calculation, or as I told you, it is simple in calculation but not so good in terms of approximation. So, what is the solution? The solution is to use predictor character method. So, explicit scheme with predictor character formulation. So, the predictor character method involves the predictor step in which we use an explicit method to obtain an approximation yn plus k raised to power p to yn plus k. So, or you can say it star also. If you see this Euler's formula, as I told you, it may be considered in a way as a PC formula, that is predictor character formula, since we are going to express it in this way, and here only we are using p equals to yn plus 1, p equals to yn plus h times f x and yn. While in character form yn plus 1 c can be obtained at yn plus h by 2 f of x n yn plus f x n plus 1 yn plus 1 p, and which is the accurate Euler's modified method, in which we are taking the average of the slope in the whole interval. In the above scheme, that is in this scheme, the formula p is a first order formula having an error of order h, while formula c, that is the character, is a second order formula which has an order of h cube. So, the above formula may be treated if required as yn plus 1 c k plus 1 equals to yn plus h by 2 f of x n yn plus f of x n yn plus 1 c k, where k equals to 1 2 3. So, you can iterate and iterate again and again. Now, we will come to multi-step predictor character formula, and this is the Milnez method. So, in Milnez method, let us assume that the value of y and y dash are known, may be given to us, or it may be computed by any self static method like Euler's method or any other method. For the points like xn minus 2, xn minus 1, xn and the initial value xn minus 3. So, we have the Newton's forward formula in terms of y prime phase u with starting node point as y prime equals to y prime n minus 3 plus u times delta, that is the forward difference operator, y prime n minus 3 plus u into u minus 1 upon factorial 2 del square y prime n minus 3 plus u into u minus 1 into u minus 3 2 upon factorial 3, and then del cube of y prime n minus 3 and so on, where this u is x minus xn minus 3 upon h, where h is the step size. So, we can write x as x minus 3 plus h times u, and from here we can write dx equals to h times du. Now, consider the initial value problem y prime equals to f of x y and the initial value is given at xn minus 3, that is y at xn minus 3 is yn minus 3. Now, if we differentiate it integrate it both sides from xn minus 3 to xn plus 1, then we can have this equation, that integration over xn minus 3 to xn plus 1 dy equals to xn minus 3 to xn plus 1 y prime dx, or when this integration will be y when I will substitute limits. So, it will become yn plus 1 minus yn minus 3 from the lower limit equals to h times 0 to 4, and from the Newton's forward formula it can be written as y prime n minus 3 plus u into delta of y prime n minus 3 and so on up to 4th order, and finally du of this. So, yn plus 1 minus yn minus 3 equals to, we are writing as this formula, and when I will integrate it, the u terms will come here because the integration of 1 will become u with respect to u. So, when I will substitute limit, so upper limit is 4, so it will become 4 times y prime n minus 3, which is my first term. Then in the second term it will become u square upon 2. So, when I will substitute the limit, u square will become 4 into 4 16. So, 16 by 2 will become 8. So, 8 times delta of y prime n minus 3, and similarly we got another 3 terms. The third term will become 20 upon 3 del square y prime n minus 3 plus 8 upon 3 del cube y prime n minus 3 plus 14 upon 45 del 4 y prime n minus 3. Now, we will replace this forward difference operator by shift operator. So, we know that from the interpolation that delta equals to e minus 1. So, I can write this delta 8 delta into 8 times e minus 1. Similarly, for del square it will become e minus 1 square, del cube will become e minus 1 cube, and this term I will take out in terms of delta only. So, when I will use it, and so 4 times y prime n minus 3 will remain as such. From here I will get 8 times e of y prime n minus 3. So, e of y prime n minus 3 will become y prime n minus 2, because we know from the shift operator that e of n, y of n plus 1 will become y of n plus 2. So, hence it will become 8 times y prime n minus 2 minus 8 times y prime n minus 3 plus 20 by 3 y prime n minus 1 minus 2 times y prime n minus 2 plus y prime n minus 3. So, this is coming from this e minus 1 square, and similarly for this term I will get 8 by 3 into y prime n minus 3 times y prime n minus 1 plus 3 y prime n minus 2 minus y prime n minus 3, and then this term which we have taken out already, that is 14h upon 45 del 4 of y prime n minus 3. Now, after simplification, here we are having 4 times y prime n minus 3, here we are having minus 8 times y prime n minus 3. Similarly, here I am having 20 by 3 times y prime n minus 3, and here minus 8 by 3 times y prime n minus 3. So, after simplification I will get that yn plus 1 minus yn minus 3, that is the left hand side, equals to 4 times h upon 3 into twice of y prime n minus 2 minus y prime n minus 1 plus 2 times y prime n plus 14h upon 45 del 4 of y prime n minus 3, or I take this the term yn minus 3 in the right hand side. So, I will get this equation, and let us denote that this term which I have taken out as E1, that is the error in predictor, and this is given as by this expression, that is 14h upon 45 del 4 of y prime n minus 3, and this I can say it is of order h5, that is by the Taylor series 14h raised to power 5 upon 45 into fifth order derivative of y at some point xi1, where this point xi1 exists between xn minus 3 to xn plus 1 in this interval. So, thus the formula yn plus 1 equals to yn minus 3 plus 4h upon 3 to y prime n minus 2 minus y prime n minus 1 plus 2 times y prime n is called the Milnez predictor formula or the extrapolation formula with error of order h raised to power 5 given by this expression. Now, we need to derive corrector formula. So, from here we will get the value of yn plus 1, but that will be the predict value. We have to correct this value, and for this we need corrector formula. So, for the corrector formula again we will consider the same initial value problem, but with different initial point. So, now we will consider initial point as x of n minus 1. So, and we consider that y at x equals to xn minus 1 equals to yn minus 1. Again we will use Newton's forward formula with the starting node xn minus 1 in terms of y dash and u. So, it is given by this expression y dash equals to y dash n minus 1 plus u times del y dash n minus 1 plus u into u minus 1 upon factorial 2 del square y dash n minus 1 and so on. So, we have taken it up to del 3, and here u is x minus xn minus 1 upon h, or I can write from this equation x equals to xn minus 1 plus h times u. So, it will become dx equals to h times du, which is the same as in predictor formula. However, range is different. In the predictor we were having the range from xn minus 3 to xn plus 1, but here we are using the range from xn minus 1 to xn plus 1. So, we are using here only 3 steps, wherever in predictor formula we were using total 4 steps. So, we have again the integral over xn minus 1 to xn plus 1 of dy equals to integral of y prime dx over xn minus 1 to xn plus 1. So, in the same way as we did in predictor formula, we can take this range as yn plus 1 minus yn minus 1, and this is equals to h times integral 0 to 2, because you can see earlier it was from 0 to 4 in the predictor, y prime n minus 1 plus u del of y prime n minus 1 plus u into u minus 1 upon factorial 2 del square y prime n minus 1 and plus third order and fourth order term and du of this. So, finally, after integrating it over u with respect to u and putting the upper limit of u as 2 and lower limit as 0, it is coming out as h times 2 times y prime n minus 1 plus 2 delta y prime n minus 1 plus 1 by 3 del square y prime n minus 1 minus 1 upon 90 del raised to del 4 y prime n minus 1. So, again we will replace this forward difference operator by the shift operator, that is we replace del by del equals to e minus 1, and we will get this expression. And here again, like we have done in the earlier step, we will take this 1 upon 90 del raised to power 4 y prime n minus 1 outside the bracket. So, we have done it here. After simplification, it is coming out as h by 3 y prime n minus 1 plus 4 times y prime n plus y prime n plus 1 plus e2, where e2 is the error and it is of the order h raised to power 5, which is similar to the predictor one. So, the formula yn plus 1 equals to yn minus 1 plus h by 3 into y prime n minus 1 plus 4 times y prime n plus y prime n plus 1 is called the Milnez corrector formula with error, an error of order h raised to power 5. So hence we are having character formula as this one. From here we will get an initial value or a predicted value of yn plus 1, which will be corrected by the corrected formula, this one which we have just derived. So combination of these two formulas are called Milne's PC formula, predictor corrector method. So let us take an example. So we need to solve the differential equation dy over dx equals to x square plus y square minus 2 for x equals to 0.3 by Milne predictor corrector method. Compute the starting values at x equals to minus 0.1, 0, 0.1 and 0.2 by the Taylor expansion about x equals to 0, where y0 is 1, taking first non-zero terms, 4 non-zero terms in the Taylor series expansion. So here y0 is 1, f of xy is x square plus y square minus 2, that is my y prime x. So basically what I am having? So y prime is f of xy and it is x square plus y square minus 2, and it is also given that y0 equals to 1. So now y prime 0 will become 0 square plus 1 square minus 2, because it is f of xy and it is coming out as minus 1. Now I will calculate y double prime. Y double prime x will become twice of x plus twice of y into y prime. So it will become twice of x plus twice of y into x square plus y square minus 2, and when I will calculate the value of y prime at double prime at 0, it will be 0 plus 2 times y at 0 will become 2, 0 plus 1 minus 2, so minus 2. Similarly, I will calculate y triple prime at 0, and again I will differentiate this with respect to x, and I will substitute the value of y prime from here in the expression, and it will come out finally as 0. I will also calculate, as I told you, in the Taylor series expansion we will use first 4 terms. So I will calculate this value and this will come out as 12. Now after calculating these values, I will use the Taylor series expansion of y about x equals to 0. So yx can be written as y0 plus x times y prime 0 plus x square upon factorial to y double prime 0 and so on. So substituting all these values, I will get yx, which is approximately equal to 1 minus x square plus x raised to power 4 upon 2. After getting this particular expression, I will calculate the value of y at minus 0.1, 0.1 and 0.2. So once I will calculate it, I will get y at the point x equals to minus 0.1 equals to 1.09, y at x equals to 0 again coming out as 1, which is also given to us as an initial condition. Then y at 0.1 is 0.89 and y at 0.2 is 0.7608. Now I am having all these values of y at these points, these 4 points. So I will calculate the value of y at 0.3 using the Milne predictor formula. So I will put the value here in this formula, and after simplifying it, I am getting this value as 0.6149. Once I will get this value, that is the predicted value of y3. Now I need to correct this value. So for this I will use corrector formula, which is given by this particular equation, that is yn plus 1 equals to yn minus 1 plus h by 3 y prime n minus 1 plus 4 times y prime n plus y prime n plus 1. So after using this, the corrected value of y at x equals to 0.3 can be obtained as 0.6149. So in this way we can apply the Milne predictor corrector method for solving ordinary differential equations. And here, as I told you, we should know the value of y at more than 1 point. In this Milne method we should know this value at least at 4 points, for which either given to us or we need to calculate using Taylor series method or Euler's method or any other method. So this method is multi-step method and it is more accurate compared to the single step method, since the accuracy in this method of order h raised to power 5 in predictor as well as in corrector formula. And hence we can use larger step size for computation when compared to the Euler's method, where for getting a better accuracy we need to use a smaller step size. So with this I will stop the discussion about this method. Now since it is the last lecture, so I would like to tell you about few references which I have used for making all these lectures. So the first one is the book Applied Numerical Analysis by Gerald and Whitney, and it is, I have used the 6th edition of this book. The other book is Numerical Methods for Scientific and Engineer Computations by Jane Enger and Jane. Moreover, I have taken some of the notes of Professor S. Bhaskar from IIT Bombay and the notes of his course Introduction to Numerical Analysis, which is online at IIT Bombay website. And the last references which I have used, the book Elementary Numerical Analysis, an Algorithmic Approach by Conte and Deepoor. That is, and I have taken the 3rd edition of this book, which is published by McGraw-Hill. So these are the references which I have followed in this course. Apart from that, I would like to acknowledge few people. The first of all, I would like to acknowledge Education Technology Cell IIT Roorkee, especially Professor B.K. Gandhi, the coordinator of PT Cell at IIT Roorkee, along with his team, Dr. Nivedita, Sarath, Mohan and other people who have along me during the shooting of this course. I am also thankful to Program Implementation Committee NPTEL, and in the last but not least, I am very thankful to my teaching assistant Ms. Savita, which is also a PhD student at Department of Mathematics IIT Roorkee, and she helped me for preparing all these slides for this course. So thank you very much.